Hello, everyone. We will be starting in about 2 minutes, so get ready. So, hello, everyone. Welcome. Thanks for joining, and welcome to our virtual AI meetup. I believe it's number 12. My name is Marek Modrý, and as one of the MLMU organizers, I will be your host today. It's great to see you here in such a number. We already have more than 130 viewers, both on Zoom and YouTube. And so just let me quickly recap, if this is your first meetup, the main communication channels. We have a website, MLMU.cz. We have a Facebook profile, Machine Learning Meetups is the name of the profile. We also have profiles on meetup.com, which you probably know. And we also have a Slack workspace where you can join and communicate with others whenever needed, not only during those meetups. Also, if you haven't heard of our community before, believe it or not, but we have organized almost 100 live events in the last 6 years in Prague, Brno, Bratislava, and Košice. And of course, if you have any recommendations, let us know either through our email or social network profiles or just any channel you find. We are very open to any suggestions. Also, if you have any topic or a recommendation for a speaker, or you would just like to join our team and help organize this community, just let us know, and we are really looking forward to your feedback. Before we start, let me also say that we are really grateful to our partners, Seznam.cz, Konica Minolta, SAS, Rosum, and Datasentics, who are really helping us building this community. And without them, we wouldn't not be where we are today. So thanks to them. And now to the main point of our meeting today. Today, it's my great pleasure to welcome people from Seznam.cz, who will introduce you to various challenges they tackle in their research. And we will see 4 short talks. But just let me remind you, if you have any questions during those talks, please ask at Slido, which is slido.com, and enter MLMU as a code. It's just a security measure because there is so many of us, so we cannot just ask loudly. Or if you have any other issue, you can also use the chat either on YouTube or here on Zoom. So also once we go through all the talks, we will not stop the event, and we will continue with some networking where you will have a chance to talk to the speakers, to other people and so on, but I will let you know more about this once it's closer. So now let me introduce Ondra Bednář and Marek Soukup, who will start with their talk on operational research and auction mechanism, which will be our first talk today. And once again, if you have any questions, use Slido or shoot it at one of the chats, either in Zoom or YouTube. So thanks again, and I'm passing the word to Marek. Just let me stop sharing. Yeah.
Right. Thanks for the introduction. I hope you can see my slides.
Yes, we can.
Cool. Thanks. So let's start. Welcome, and let me tell you something about operations research, data science, and how we use these two together in Seznam. So first, here's what you'll learn today in this presentation. So first, I will define operations research, introduce its role in Seznam. Then I will talk about how we use the way we use machine learning in operations research in Seznam. And after that, my colleague Ondra will talk about auctions, and he will walk you through one particular project that we're currently working on. Now, what is operations research? It's a subfield of mathematics that applies advanced analytical tools to support decision making. So basically, it's mathematical optimization applied to practical problems. And what operations researchers do? Well, we optimize processes, and we help management in an organization to solve their problems. So a member of a management may come and say, well, I have this and this problem, and I would like you to use some formal tools and data to help me solve it. And our task then is to understand the problem better, which involves consulting and exploratory data analysis, perhaps some data mining. We formalize the problem, find an optimal solution or solutions, and then crucially, we have to implement the solutions. And that's where we use machine learning, because especially in a data-intensive environment, which Seznam is, the mathematical optimal solutions don't have to be necessarily implementable in practice. So we use machine learning to implement the theoretically optimal solutions. Now I will introduce the trading mechanism that Seznam uses. And the core business of Seznam is selling advertisements. And this is how the process of trading advertisements looks like. So imagine you enter a website. For example, you want to read a news article. And at the moment you enter the website, a request is sent to a marketplace called an ad exchange. This is a mechanism that is owned by Seznam and run by Seznam. And the ad exchange collects candidate advertisements, offers of advertisements from advertisers who want their adverts to be displayed to you, who's browsing the website. And the ad exchange runs a selection mechanism, typically an auction, more about it later, that selects the best advertisement. And once the advertisement is selected, it's sent back to the website and displayed to to the customer. Yeah. And this whole process takes just a few milliseconds. So this is high frequency trading. There are approximately, there are thousands of trades taking place every second, and we have hundreds of millions of displays per day. Now, what is the role of Seznam? What is Seznam doing? We are trying to reconcile the interests of three parties. First, there are potential customers who are browsing websites and potentially they want to buy certain products. Then there are firms who want to sell their products to the customers. And that's why they set up advertising campaigns, because they want to deliver the information about their products to the potential customers. And Seznam is facilitating this trade. So Seznam is acting on behalf of the firms. We help them set up their campaigns and to deliver their information about their products to the right customers at the right time for the right price. Now, this trading system is not that straightforward. Actually, it's pretty complex because there are multiple types of websites. For example, Seznam owns several websites, but there are also external websites with owners different from Seznam. And if we want to sell ads, if we want to display ads on the external websites, we have to pay some fees. Then, for instance, there are many types of advertising campaigns. For example, the advertisers may want to pay for click if their ad is clicked on, but they might also want to pay for an so-called an impression, which is one display of their advertisement. Then there are so-called guaranteed campaigns, which are prepaid, meaning that an advertiser comes and says, well, I require this number of clicks, and I pay this much money for that, and you, Mr. Seznam, well, give me that number of clicks. And there are also real-time bidding campaigns where the advertiser comes and says, well, I have this budget, and you, Mr. Seznam, give me as many clicks as possible. There are also external marketplaces, so this is multi-stage process. There are multiple selection mechanisms at different stages, so it's fairly complicated system. Now, what the role of operations research in this whole system is, so as I have said already, Seznam aims at delivering the information about the firm's products to the right customers at the right time for the right price. And the right price is important for operations research because what we do, our tasks are typically about pricing and allocation. So we decide which advertisements to show to whom, at what time, and for what price, which is this pricing. For example, we may have to consider the minimum price that we are willing to sell the advertisement for. This is called reserve price, and Ondrej will talk about it in more detail later. And I have already said that operations research is about decision making, and our decisions are what to sell, when to sell, to whom, and for how much. However, there are thousands of decisions we have to make every second. So operations research in data-intensive environment is about creating automated policies, meaning an automated decision-making process that we have to find certain rules according to which we decide. Right. And now, what is the role of machine learning in this? I'll give you an example of one task, which is automated bidding. The advertising campaigns who want to deliver the information about their products to the customers, they make their offers automatically because they have to do it very, very frequently. So they set rules that send their offers. They set the prices they are willing to sell their adverts for. So we can take this as an optimization problem. Let's say that the advertisers maximize clicks. Let's assume that, subject to their budget constraints because the money they are willing to spend is limited, and subject to some targeting constraints because the firms, they want to address some audience only because they have different products and they don't want to sell those products to anybody. They want to everybody. They want to target at some segment of the customers only. So they face some targeting constraints. And we can formulate this problem as an optimization problem. However, the implementation must be automatic. And that's how we use machine learning. So we can, for example, use logistic regression. If we want to predict the user response, we want to, for example, predict the probability that the advertisement will be clicked on. More about that later. We can also use some gradient-based methods for dynamic price adjustment. So we can have some mechanism and we set up some initial price, and then the price is adjusted in real time according to some function that we have to set up. So we have to invent a function that we're supposed to maximize through the process, and then we use gradient-based method to adjust the price. And also, it's possible to use reinforcement learning techniques to find optimal policies, optimal bidding functions for the advertisers. However, this is just an example of few methods that we can use. So really, sky is the limit here in this case, because there are multiple opportunities to learn to use machine learning. Okay, and now my colleague Ondra will tell you something about auctions, and he will show you one particular project that we've been working on. Okay, so thank you.
Okay, can you hear me? Yes. So thank you, Marek. My name is Ondrej Filip, and I work as an auction researcher in Seznam.cz. So today I would like to tell you something about the reserve price project in auction research, in operation research in Seznam.cz. So let's dive into it. So first I will a little bit explain about what the environment is and what the auctions are really about. And then when we will know the problem, I will talk about how to solve the problem. So first we should know what the auction is. So the auction is a sale of a property to the highest bidder. So that's a definition by Merriam-Webster dictionary, and economics provides us with other definitions, but usually more difficult. So I think this one is actually quite good. Now, in auctions, there are usually bidders, sellers, and auction goods. In our case, the bidders are the advertisers. The sellers are the publishers, or in our case, for the sake of simplicity, it's Seznam. And the auction goods are the impressions, that is the displays or the views of the advertisement. Okay. Now, in Seznam, we run a sealed bid second price auction. Now, sealed bid means that bidders cannot see other bidders' valuation. They cannot infer what they think and how they value the good. So it's the opposite of the open style or open bid auction, where, for example, all the bidders are in the same room and they can see what the other people think of it and so on. Second price, it means that, of course, the highest bid wins, but the winner doesn't pay the highest bid, but actually pays usually less, or always less, either the second highest bid or the reserve price. Now, what the reserve price is? Reserve price in second auction, it's a tool. It's a tool of the seller, and we also call it threshold or reservation price. It's all the same. It has two functions: to prevent selling the good under the seller's value, and to maximize the revenue. Because when the seller is able to set the threshold or the reserve price between the first bid and the second bid, then the buyer, the bidder, doesn't pay the second highest bid, but he pays the reservation price, which is higher. So that's how you can increase the revenue. Now here is what I said in the graph. So on the y-axis there is revenue, on the x-axis there is reserve price, and you can see that if the reserve price is lower than the second highest bid, then it has no impact on the revenue because the winner pays the value of the second highest bid. But if the reserve price is between the second highest bid and the winning bid, then it has a positive impact on the revenue, and therefore that's the role. That's the way how you can maximize the revenue. On the other hand, if the reserve price is larger than the winning bid, it has actually a detrimental effect on the revenue because then no good is sold, and therefore there is no revenue in this auction. So the revenue is zero. Now let's move forward. How to our problem? How to set the reserve price? So I will speak about the project that we got here. So we had a task to remove the lowest quality advertisements without decreasing revenue. So now first I must mention that the price in our auction is actually a product of two numbers. The bid price, that's what the bidders bid, that's pretty clear. And then there's a quality score that actually that is actually determined, or it's a number calculated by our colleagues, researchers also, by machine learning, and the number determines the relevancy and quality of the advertisement to the user, to the reader or viewer of the advertisement. So if the price in the auction is low, it means that it is actually low quality or irrelevant advertisements to the reader, and it can maybe bother him. Now, so there were many suggestions as how to solve this issue, because we didn't want to bother the user, the consumer, with irrelevant advertisement, but we also didn't want to lose the revenue. Us in research, we wanted to stick with the concept of the second price auction, so we wanted to do it with the reserve price tool. Now, we were considering many approaches, but I think the two most salient or two major approaches that we were considering were these two. So the first one is, I would call it a classical approach. We call it Meyerson's formula because it's named after Roger Meyerson, who obtained the Nobel Economics Prize for his contribution to operation research. Yes, and actually the idea of this approach is that while the reserve price removes the cheapest winning bids in some auctions, it should more than compensate for it by setting the reserve price between the first and second bid. The approach is based on the bids distribution in given category of auctions. That is, you split basically all the auctions. We have, like Marek already said, we have 100 of millions auctions a day. So we split them in some categories based on the websites and so on. So so we set the reserve price, or the reserve price should be set in the auction. Now, if we look at the formula, so the R star here, R star is optimum reserve price. X0 is minimum valuation of the good by the seller. And the CDF is cumulative density function of the distribution of the bits evaluated at the optimum reserve price over probability density function, again, of the distributions of the bit evaluated at the optimum reserve price. As you can see, the formula is not very handy because we have the optimum reserve price on both sides of the equation, but it is solvable numerically. So yeah. So this is the approach. Yahoo, for example, uses this kind of approach to setting their reserve price. Now, here I wanted to show you the distribution of the bits in one such a category. On the x-axis, there is a cost per 1,000 impression, CPT. And on the y-axis, there's a bits share. So it's normalized to 1. It should sum up all the bits to 1. And as you can see, it looks log normal. Theory says it's log normal. When we did some computations, so we were calculating or fitting the many categories to different kind of distributions. So the log normal was most of the time the best theoretical fitting to the empirical distribution of the bits. Now, yes, and this dashed line should be a reserve price. We have to determine where to put it, right? So now the second approach is the machine learning approach, or we call it machine learning approach. And this approach is different because it sets the reserve price for every single auction. So yeah, so the seller, yeah, the philosophy of it is a little bit different because the seller is a sort of a bidder who always wants to be the second one. He never wants, you as a seller, you don't want to set a reserve price higher than the winning bid because you lose. So yeah, you need to estimate the reserve price so that it ends up at the second place. Now, how to do it? The approach it is estimated as the reserve price is estimated as a linear function of auction attributes. There can be generally 3 types of auction attributes. First of them, it would be the features of the website. Second one would be segment of the consumer or the reader, and the third one would be about the user behavior. So, and because it is because this approach is setting reserve price updated for each new auction, also the weights of these attributes or of the features have to be updated. Now this is done by a stochastic gradient ascent after each auction. Now I will show you in the next graph. So this is a similar graph like I showed you previously. On the y-axis there is revenue, on the x-axis there is a reserve price, and the black line here is the revenue function. As you can see, there are 2 points that are not differentiable. Here, this one, right? There's an angle, and here is discontinuity because it follows here, and therefore the revenue function has to be approximated. This is done by a so-called plus function and a reverse sigmoid function. Now the stochastic gradient ascent is of course updating its weights of the features to always place it somewhere here to the top to maximize the revenue, of course. Now let's go for, yeah. So the results so far. We've been testing Meyerson's formula because the objective of our task that was given by the product manager actually requires removal some of the advertisement. So, and the machine learning approach is trying to avoid removing some of the advertisement. But therefore we started to do the Meyerson's formula. And the results on the subsamples is that we remove 5 to 15% auctions where the reserve price is larger than would be a winning bid, and the revenue effect would be more or less neutral. On the other hand, the Upnexus machine learning approach, the authors of the paper that it is based on, they claim to increase revenue compared to situation where there is no reserve price by about 35%. And this is also achieved by the fact that they avoid removing the winning bids, like in the Meyerson's formula. Okay, I think this is the sources that the presentation was based on. And yeah, I'm looking for your questions in the Slido, and I will pass the words to.
Thanks, Ondrej. Let me just quickly share the screen with the questions, which is here. I hope you can see that. And the first question is, do you actually use reinforcement learning, or is it just an option you know of?
I assume this is on me. So currently, no reinforcement learning is implemented in what operational research is doing. However, we have a project which is in an early stage of development, and we plan to at least test machine reinforcement learning. In that case, it's actually automated bidding for one specific segment of advertising campaigns. And currently I'm working on a prototype in a simulated environment. So I hope I have answered that question.
Cool. So we are looking forward to an updated presentation.
Me too.
Yeah, so another one is, did you try to use tree-based models instead of logistic model, prediction of response?
Right, so we will pass this question to next speaker, I assume, because operations research is not doing this kind of prediction explicitly. We use what another team is developing, and their talk will come next. So
okay, so for now we will skip them. And then we have a third question, which is also from Arsen. If you are worried about model interpretation, maybe you could consider Python's facet library. You want to comment on this recommendation? Or is it also on Honza as the next speaker?
No, I'm not sure whether it's on me or Ondra.
I wasn't worried about model interpretation, so yeah.
Honestly, I don't understand the question. Sorry.
Okay, so there is also link. We will definitely keep this link for later and share it with the speakers if you want to check on this. Also, Arsen, if you want to clarify the question, feel free to shoot it in one of the chats so that perhaps one of the guys can answer later. And since we are out of questions and right on the time, I will pass the word to Honza and his talk on the click prediction. So let me stop sharing.
Okay, I hope you see the screen, right?
Yes.
Okay, hello, my name is Jan, and I'm leading a team at Seznam.cz, which is dealing with ad relevance. So I will talk mostly about ad click prediction, but maybe if I have time in the end, I will speak also about a few other problems we are facing. About the ad click prediction, the structure of my talk is first briefly introduce what it is about, and then I will formulate it as a supervised learning problem. But then I will also speak about how it is not that simple, that there are a lot of data biases, and actually it's not completely a supervised learning problem at all. So so first, for introduction, well, we are actually dealing with two major types of advertisements. One of them is occurs in our search engine. That's a lot of you know probably, and namely, if user searches something, some query, then we display, of course, some organic results down below, but because we need to have some revenue, we also displayed sponsored ads, which there are 3 here on the top. So they're basically similar to the organic results in this case, but they don't have to be. There are also, for example, these product listing ads on the right, which contain not just textual information, but also some picture of a product which relates to the query the user is searching. The second type of the advertisements we are dealing with is display advertising, and it doesn't show up on the search engine, but it shows up when you are browsing some content on the internet. So in this case, it is a media website, and there are 2 advertisements on the left and on the right. So I will be speaking about both of these problems because many times the ad click prediction is used somewhere in between. And as you have already seen or heard from Marek and Ondra, actually the processing of or the delivery of the advertisement takes place in several stages. So the user makes a request, and we want to sometimes display an advertisement. That is, we want to make an impression. But in between, there are 3 stages which we need to do in a few milliseconds. The first stage is candidate selection, which in case of search engine or sponsored search, it's usually based on keywords matching, which will be later spoken about by Xenia in the next talk. Then there is this central step, which uses some machine learning magic, and I will be speaking about it in this talk. And then after computing some kind of quality score, we use this quality score in the auction, which is used to select the ad we want to show to the user. So let us focus on the central stage. So we have some ads which are preselected somehow from the previous step. Then we use some machine learning magic which computes ad click probability, and as you have already heard, it's then multiplied by the price, the maximum price, which the advertiser is willing to pay for when the user clicks on the ad, and this product is then used in the auction. So how this central magic actually works? Well, actually, I will not tell you about that, but to answer the question which occurred already, we use both logistic regression and tree approaches. So we are using both, but there are many other other possibilities, and it's more complicated than that. But regardless of which argument we are algorithm we are using, it can be formulated as a supervised learning problem. That is, we are given an ad here that and we are given a label which is a user response in the form of click or not click, and we are giving some features which we are using to we are feeding to the algorithm to to predict the user response. So these features can be of different nature. It can be some features of the ads, for example, textual information. It can be information about the page on which the advertisement is shown. So some text or keywords inside the page, or it can be, in case of sponsored search, it can be the query the user has typed, or it can be some information about the user, like behavior targeting or click history from the past. But it can be also information about the world. For example, if this raining right now, then maybe umbrellas will be sold more often than other types of products. So these are the features we are using, and they can be either IDs, it can be some statistical information from the past, and so on. Well, and our goal is predicting the probability of the click. It means we are actually using log loss for our optimization. So it leads naturally to the logistic regression. But we need to compute other metrics as well. So when we are evaluating our model, we need to compute also. We are using, for example, area under research operator characteristics curve. So AUC, and to evaluate whether the learned model performs well on the testing data or not. But we are also interested in online metrics when the model is deployed in the end. So we are, well, it depends, of course, on the type of ad and so on, and on our business model. But lots of times we are measuring click-through rate. Then it's possible to measure profit. Obviously, that's maybe the ultimate metric. But also maybe we are interested in time spent. If, for example, Facebook could be maybe maximizing the time spent on their pages. Maybe if we are a search engine, maybe we want to minimize actually the time spent by the user to find whatever he's searching on. So it depends. And of what's another important metric is conversion rate. That is the ratio of the clicks of conversions versus the number of clicks which occurred on which the model is doing. So these are the metrics we are using. And well, actually, I want to I just wanted to also say that the one of the maybe more very important but very difficult problems is also aligning these metrics together, so that if we want to make it so that the minimizing the log loss somehow corresponds to maximizing the profit, and it's not easy, and it's one of the problems we are dealing with. Okay, and another thing I want to stress here is that we are not interested in just ranking or of the ads, so making some ranking of them, and we are not interested also in the classification to just click or not click. We are really interested in the number, in the probability itself. And why is that? Is because we are not alone. Our component is actually living in a ecosystem, be it other advertising companies which are competing with us in the same auction, or be it organic search on inside which actually or besides which our ads are shown, or be it other teams or other components which are optimizing something, and maybe they want to use the probability itself, not just classification, or be it our customers, the advertisers, which are with which we are making business. So at Click, I said previously that at Clidiction is a supervised learning problem, but there are some complications which make the problem harder. Well, actually, there are a lot of data biases, and I will just focus on one or two of them. And well, just to show you on a graph, if we measure the click-through rate, that is the number of clicks versus the number of impressions per position in search, in sponsored search on the right. So there are 3 positions actually, and if we measure the click-through rates per position, we notice that the first position gets much more clicks than the next positions, and this graph can be actually decomposed into 2 factors, and each of them has different cause. The first one can be called position bias, and the other can be called selection bias, and these have different causes, so I will talk about them separately now. So the first one, the position bias, it's actually determined by the ad location in a page, or even if there are more positions at one location, it can be determined by position of the individual ad inside this location. So it somehow reflects how much attention the user pays to a certain location. In this case, the solution to we want actually to get rid of this bias, right? Because it's influencing our data and makes the machine learning on this data more difficult. So how to deal with this? Well, it's actually not so much problem depending on which features we are using. In for some features, it's not problem at all. For example, if we use some ID features, we just it can be simply solved by adding a position feature into our model, and that's it. But if we use statistical features, we want to debias them, to get rid of the bias inside the features, and this can be easily done. This can be done by using information retrieval theory, namely click models. About the second bias, it's a bit more difficult than that. The second bias is actually determined by what we displayed. So it's determined by the system which was used to select the advertisements. So, for example, if the model is because the results are fed from the model to the auction, the best advertisement, the most relevant, usually win, or a lot of times win the auction. So actually the first position gets the best advertisement. So that's why the highest click-through rate is on the first position. So the solution to this problem is not that simple, but it's possible. One of the possibilities is, for example, that we can choose half of our requests to show completely random advertisement, and then use this debiased data completely without bias to learn our model. But that's probably not doable, because we use almost half of the profit, right? So that's not a good solution. So another possibility is to use some counterfactual learning. Well, counterfactual learning, it sounds fancy, but well, actually it could be that it's not that difficult. Actually, it's we can use, for example, inverse propensity scoring, which is actually a cross multiplication, but by inverse of some number based on the randomization of the model. So it can be done. But well, actually, for this selection bias, actually it's connected to another thing, which causes the whole problem to stop being supervised learning problem at all. That is, it can be best visualized when you think about what happens if a new ad arrives. Well, if there is a completely new ad, we don't have any feedback data. We don't have, it was not shown before, so it was not clicked, so we don't know anything about what the feedback will be. So, well, that again, a few solutions to this problem. Well, first one is we just use some average prediction, and that's it. So that's one possibility, but not very good one. The other possibility is at least to use content features. That is, we have some information about the text of the ad, or visual, how the ad looks like. So we can use it to compute the probability just from these content features only. So that's a better possibility. But another possibility is to actually explore. Well, exploration, you maybe heard about exploration exploitation dilemma. So, well, exploration exploitation dilemma, it's dealing with two extremes. One is a completely new page or ad or query, in which case we can't use any feedback. So we need to somehow try different possibilities and try to explore what the user feedback actually is. The other extreme is that we have a page, ad, or query on which we have lots of data, in which case we can exploit the data which we have and we don't have to explore at all. And of course, most of the times we are somewhere in between. So we are sometimes we are exploring, and sometimes we are exploiting. So, well, the most of the time, this how to proceed. It takes two steps to to make this work. First step is that we want to model the uncertainty of our prediction. And it can be either we can use a simple heuristics on sometimes if we use, for example, Bayesian modeling, we get it from the model itself. So then it's easier. And the second step is actually using this uncertainty to explore or exploit. So there are many algorithms to do this. Well, Thompson sampling or after confidence bandits. That's 2 of them. So that's it. Well, and lastly, I want to just briefly mention that there is another problem that we are dealing with, and that is that the times are changing. That time is affecting a lot of things in our model. First, the new ads arrive, as I already said, but the models are also aging, right? So the traditional approach that we have some pre-packaged data that we want to feed into our magic machine learning to learn a model and then deploy it into the production. And then we can just, and that's it. Then we can just, go on vacation. It doesn't work that well in our case. So we need actually to do something more complicated, that we repeat these steps on and on again. So and this approach obviously has some major advantages, that the models are trained on recent data, so they are young and fresh, and they are working well on in our case. But obviously there's also some major disadvantage, and that is that we can't go to holiday. So okay, so well, these 2 types of models can be have different advantages and disadvantages. But yeah, that's probably it. I don't have too much time anymore, so I just want to skip that. This is not the only problem we are working on. There are really lots of other problems which are either connected, and some of them were already mentioned. Some of them will be mentioned in later talks. So yeah, so that's it. Thank you for your attention.
Thanks, Honza. Hopefully, if you share the slides later on, we will share it with the crowd, so you can check what was skipped and perhaps think about it a little bit more. And I will share the questions. Hopefully you can see the correct screen. And the first question is how computational intensive the task is. What is an approximate volume of the training data you use, and what technology stack do you use to collect the features?
Yeah, that's a very good question. Well, that is actually why we are not using any fancy algorithms like neural networks, or at least not very intensively. We are using it just to some small tasks which are connected to the ad prediction, but we are mostly using simpler but effective algorithms. For example, Wopal Webbit or CatBoost gradient boosted framework. And for the collection of the data, well, we are using Spark and aggregating data and computing some statistics and so on. So
Okay.
if I address this question. Okay.
Thanks. Do you often observe a shift between an offline and an online test?
Yeah, that's a major problem actually. So it often happens that we are very optimistic about the performance of a model in offline, but then when we deploy it online, we actually see that it's not doing that well. Maybe it can be doing well in some metrics like click-through rate, but it's not doing that well in terms of profit. So it's quite difficult to make it aligned, and so we are working on better metrics to measure offline, like not using the for example log loss or AUC simply like that, but to somehow to do some other metrics. So, but it's not easy. Definitely, we are struggling with it.
Okay, thanks. And are the results of tree-based model and logistic regression similar? Does one approach works much better in some cases?
It depends on the features. For example, we are able to obtain as good results or almost as good results by a logistic regression if we do a lot of feature engineering. But it's easier to do it using tree-based models. We can use simpler features. For example, you can feed, instead of feeding a number to the logistic regression, you can choose to make bins out of this number and feed this as a feature to the logistic regression. So it somehow simulates what the tree-based model does. So and about the second question, it's hard to say.
Okay.
It also depends on how fast we want to go. So, for example, Vopal Webbit is still a bit faster than the tree-based model. So it depends on how fast we want to go.
Okay. And the last question for sake of schedule. So how are you training Sklik model to optimize for profit or time spent? Do you frame it as a multi-objective problem?
Well, we actually try to make one learning objective which reflects the business metrics which we are interested in. So we are not using multi-objective optimization itself, but there are some and we are also not actually optimizing on time spent. So that's yeah, that's probably.
All right. So sorry for not answering to all the questions, but if you stay to the very end, I hope you will be able to find answer there and ask the questions there. So thanks, and let me pass the word to Xenia, who will continue with the third talk. And yeah, you should be able to share the screen. Awesome. I can see the screen, so the word is yours.
So hello, is it okay? Yeah. Good. Hello. My name is Xenia Shakurova. I am a research team lead at Seznam.cz, and my tonight talk will be about our attempt to create an automatic system for generating keywords for text adverts campaigns. My colleagues previously told you about advertising systems and how do they work, so I will just shortly repeat that. Then I will explain our problematic and our goals and what problems we faced. After that, I will tell some details about our approach and what results have we achieved. So let's start from the very beginning. A user comes with a query. For example, query Samsung Galaxy Watch will lead us to this kind of SERP with some results, some text advertising, and some image advertising. So our area of interest is here. We dealt with text adverts in search. And how do we decide what adverts to show? Well, let's imagine that our client has an e-shop and he sells some watch and some smart TVs. So he wants to show an advert. So he has to create a campaign, which is a pair of many pairs of URL and a set of keywords. And he wants these keywords to match some queries. So, for example, when we have many advertisers, so they construct our advertiser database. So, for example, query Samsung Galaxy Watch here will perfectly match our advertiser because he has exactly the same keyword. But another keyword, for example, cheap smart TV, will not match because he wants to sell just expensive smart TVs. So this is just his product focus. Of course, there are many advertisers that sell the same thing, so we need to choose what adverts to show. And the system is rather complicated, and my colleagues showed it before. We have this matching algorithm here, and then there is some text relevance model that filters all bad adverts. Then we predict some CTR to rank the rest of adverts, and only best adverts go to auction system that chooses the last list of adverts that you see in a SEP. So our task now was about this very first module that decides which adverts to show and about this matching system. So where's the problem in that? The problem is that many e-shops just do not have keywords, so they are not our clients. And they do not have these keywords because it is very expensive and time-consuming to create them. So that's why we decided that we need some system that will generate keywords automatically from just a given domain. And what are we going to do with it? Well, we have an existing database of advertisers' keywords, and it is rather big. It contains a little bit more than 100 millions of keywords. I mean here a pair keyword and URL. And it seemed to be a best solution to train something on this data. But unfortunately, soon we stumbled upon a problem. Problem was that these data were really very dirty. There were many duplications, some bad tokenizations, formatting errors, and so on and so on. So eventually, just the fifth spot of the whole database were some valid keywords. And also, we should filter phrases that were never searched because we just do not need to work with them. So when we filtered them, there are only 1% of the data left. But still, we thought it is not so bad, 1 million of keywords. So therefore, we looked at the data more closely. And what we've got that these keywords are really very specific, and advertisers did not try their best to make them good, I would say. Many advertisers just tried all possibilities, like just change word order and so on and so on. Also, many advertisers just used competitors' names and labels as their keywords. So they cheated a little bit. But we also noticed some interesting things like that a keyword number decreases as we got far from homepage, and that keywords from homepage are usually more extensive, they're more common, and they usually are not in the content of the page at all. The last thing was that we know already that query language differs from natural language at all. But language of keywords differs from language of queries also. So finally, we changed our task from just modeling advertiser database. We said to ourselves that we will not use it like at all, maybe just for some tuning. And we also wanted not to just create new campaigns, but also to complete an existing ones. And as you can notice, we need data again because we can't use advertisers database. So first of all, we decided to create annotations. Our annotation pair is some keyword and URL. It is like some relevance task, I would say. And we had some positive labels, some here, some negative labels, and some additional labels that helped us a lot. I will tell about it later. These additional labels were just like too wide meaning of keyword or too narrow meaning of keyword. For example, for a page with a gallery of smart TVs, we didn't want to choose keyword that contains a name of a particular model of smart TV. So we annotated keywords from advertisers database. And also we had some very first experiments, and we took some keywords from that experiments. Totally, we annotated about 2,000 of URLs from about 300 domains. And what was our solution? Our solution is a complex system that has 3 steps. In first step, we generate all possible candidates from our data. Then we try to filter all inappropriate phrases. And in the end, we create some perfect match of keywords and URLs on a single domain due to some requirements from product management or from this particular client. So how did the first step look like? Well, first step, most candidates were skipgrams from page content, such as URL, title, or some part of the page that we think that is most significant. Also, we use some information like which part of the page are anchors, which is not, which has some bigger letters or smaller letters, and so on and so on. Also, we noticed that some pages have poor or irrelevant candidates, and we also noticed that the reason was that they didn't have much content on these pages. So we tried to use some similarity of titles to find more similar pages and get candidates from them. But unfortunately, this attempt failed because mostly these pages didn't even have good titles. So it was just dead look. But we used not only the content of the page, we used also queries. We tried to find some similar queries to the titles of pages and use them as candidates. I should mention that we not only use skipgrams, we also tried some different algorithms like ngrams, some text rank or rake, but in the end, skipgrams proved to be the best solution. As you can imagine, that first step, this generation step, creates enormous number of candidates, and many of them are not too related. Also, if you know, skipgrams tend to generate meaningless or structurally incorrect phrases. So we needed to create some filters to remove all these bad phrases. Also, During the project, we got a claim to provide only commercial candidates. So, which filters did we use and what we've created? Well, first of all, we used search rate from logging data to identify less searched queries. Then we also used our data set of web pages to create a language model that could identify morphologically incorrect phrases. Also, we've got all commercial queries from the last year, or maybe two, and we've created an Ngram model that could filter uncommercial keywords. It is clear that there are many model names and brands that just appear and disappear in time, so we added some masking mechanism just to deal with unknown words, and it worked perfectly for us. There were many other filters, including many heuristics, but I will not tell about them now because I just will not have time for that. You can probably ask later if you are interested. And the last part of this pipeline is something I called match. Well, during the project, we also got several requirements from project managers, including that we do not want to offer the same word to more than 2 or 3 pages on a website. For example, name of a website is a good keyword for a homepage, but it is not a good keyword from a page with a single smartphone or something like that. Also, we wanted to be able to adjust the number of keywords due to domain size, and so on and so on. There are many such requirements. So we needed to create some matching algorithm that will just adjust and create the best pairing for the whole web. So how does it work? Well, imagine we have a pair, keyword, URL, and we have some price for that pair. And then we use a dynamic programming algorithm that searches for the cheapest solution for the whole domain. This price is given by some XGBoost ranker, and this ranker just ranks which keywords are better for which URLs. This model used many signals from our search engine, for example, some text relevance, some classification for keywords, some classifications for pages, and so on and so on. Also, we used different features from language models we trained, and some features from other divisions, like, for example, Zboží.cz knew which phrase is a product or can predict if a phrase is a product. And my colleague Ondra will tell about that later in the last presentation. This is how the whole solution looks like, and now we need to evaluate that. So for evaluation, we used a classic recall and precision metric. It is important to notice now that our train and test set had that feature that they had unique domains. It was a key feature due to the task specificity. Despite the fact that we had 6 labels at the beginning, we evaluated on a binary scale. We considered 2 highest labels as positive and other labels as negative. So what for non-binary scale was? Well, first of all, it helped us to understand what is going on with the model and tune it in the best way. And also it was better for annotators and help them to make less mistakes. This is 100% true. So also you can notice here that we have two metrics for precision known and just precision. So this first precision known considered only those keywords that we generated and that were actually annotated. But clearly that we generated some extra keywords. So this second precision metric considered them as false positives. We needed it to just control how much keywords we're generating and so on. And it is clear that this precision underestimates a little bit always. Well, you can see that final numbers are not so insanely high, 70% precision and 45% recall. But it is good to mention the quality of advertisers' database. So you can understand how difficult the task was. So if we evaluate keywords from our advertisers on annotations, how good will they be? Well, not so good. They have just slightly above 70% precision and recall both. And this is not so far from our numbers. So you can see that even advertisers do not create the good keyword sets. So, but in the end, like metrics are good, and you should always have some metric. But annotations didn't cover all cases, and we didn't have so much annotations. So in the end, the best model was chosen by the method. Look and tell me which model do you like more. So, what conclusions did we have? Well, first of all, handmade data usually contain many errors. You should check them and just not relate on them. This task was extremely hard to evaluate, and surely more clean annotations improved results a lot. And also we noticed how fast web pages changes and disappear in internet, because we annotated in iterations, and many times it happened that some pages just disappeared and were not in data anymore. And the last thing is that machine learning is great, but this time only hybrid of machine learning and some heuristics worked better for us. More important, only deep understanding of data helped us to tune models in the best way. So this is it. Thank you for your attention, and please questions.
Thank you, Xenia. Let me just share the screen again with the questions. Where it is? Here. Hopefully you can see the correct screen. And we have 3 questions. So the first one is the matching term-based or more likely semantic? And what if the client says not expensive TV, does it match with cheap TV or it matches with expensive TV?
Well, this matching is term-based. It is complicated because there are, I think, 6 types of matching, and I just make it a little bit easier that I said it should be the strictly matched. But for example, keyword expensive TV will match for expensive TV and the most expensive TV and so on and so on. Just you should have all terms in that query to match.
Thanks. The next question is, I'm not sure if queries as candidate sources is clear to me, but did you consider queries URL hits logs from searchers as a source of candidate terms?
Yes, we also tried that, but also the product review was that there can be some new client that just set up his e-shop, so he doesn't have any clicks, and so we needed just this like cold start for this client, so we didn't rely on this hits from logs.
Okay. And the third question is, do you have or consider having a tool that helps advertisers to choose the right keywords, input URL, output keywords in the front end?
I think that yes. First of all, we still considering how it will look like in the production. I think that now there is some tool for clients that if he puts some URL, it provides some keywords. It's not so sophisticated as our solution, but I think in the end it will look like this. So he comes with a domain and gets his keywords in front end.
Cool, thanks. This has covered all our questions, and I will stop my sharing and I will invite Ondra to the virtual stage and hopefully start the fourth talk of the day. Yeah, and here it is. Cool. So it's yours. We can see the slides.
Yes, great. Hello, everyone. My name is Ondrej, and I lead a research team at Seznam, and the team is based in Zlín. My talk will be slightly more practical than the previous ones, and it will also not be about advertisement. However, it will be about a related topic of e-commerce. It will be or it consists of two parts. In the first part, I will talk about Zboží.cz service, which is one of web services of Seznam, and about a pairing tool, which is a tool we worked on in our recent project when we wanted to improve it. And in second part, which will be longer, I will talk about 3 problems we met when we work on the project. As the title of my talk suggests, all 3 problems are related to measurement of model performance, and all of them affected the metrics of the system and the underlying model as well. So what is Zboží.cz? It's a comparison shopping engine where users can find profiles of individual products. Like here, it's a Samsung Galaxy A41 with some information about the product. But most importantly, the user can find offers from different e-shops, and he or she can choose what offer he likes and where he wants to buy the product. In our database, we have millions of products, and from e-shops, we are provided with hundreds of millions of offers. These offers are transferred to us in form of XML feed because e-shops want us to present their offers on our page. The goal of pairing tool is to pair offers to these products. There is a small catch, though, that a majority of offers don't have a product to be paired to. And the reason is that most of the offers are just too unique, and we don't want to have product pages with only a single offer, or they are of low quality. So it's something we don't want to present to users as well, and there are other reasons too. So how does the pairing work? Given the offer here, Samsung Galaxy A41 from mall.cz, which is a well-known Czech eShop. We have some structured data for the offer. And the first step is to search for candidate products in full text index. We use name of the offer and barcodes as well to do this search. And we obtained 3 candidates. The first one is the one we want to pair to, Samsung Galaxy A41, and usually we obtain goods or products with similar names like Samsung Galaxy A42, and very often it's also some accessories like the black cover here on the right. For candidates, we can compute features. The features are computed from pairs of the offer and a candidate. And these features are used to predict scores for these candidates. And once we have the scores, we can tell the best candidate. In the end, we have to decide whether the best candidate is the candidate we want to assign to offer, because for some offers, I already mentioned it, it can happen that the product is not in database, or it is in database, but full text index was, or the full text index did not retrieve it. And here I have a little question for you. If you look on the whole system, what do you think is the standard machine learning task we are solving here? I will give you a few seconds to think about it. It can be either maybe classification or ranking, or maybe something different. And before I disclose the answer, I have to say that some of you might think about classification. And when we started working on the project, we thought that it's classification too. And it was because when we started working on the project, there was already a model which was implemented as classifier, and we wanted to improve the classifier. So we started working with standard classifier metrics for imbalanced data sets, so with precision and recall. But the question is, what does precision and recall mean in the context of pairing tool? Here are our candidates from previous slide. And if you take a look on the first row, you see the Galaxy A41, which is the right product. So it's labeled 1, and it has high score, which is above threshold. So it's correctly classified, and it's true positive. Then I will skip to the last row, another phone with a similar name, which is a bad phone. We don't want to pair to. It has low score, which is below threshold, so it's 0, predicted as 0. So we are good here as well. We have true negative, but in the middle, there's the cover, which is a bad candidate, 0, but it has a high score, which is above threshold, so it's predicted as 1. And in binary classification, this situation is false positive, so an error. Again, a question, is it a real error or not? In fact, in Zboží.cz, only a single product can be paired to the offer. So this cannot happen in production. So our metrics did not capture the full picture, and we had to adjust our metrics. How did we do? We introduced a winner score, which means that we masked candidates which did not win the competition, and the cover and the Galaxy A42, and our cover became true negative because it was predicted with 0. We call these metrics winner precision and winner recall. this leads me to my question, whether it's ranking or classification. And you can see here that it's both of them. We first rank candidates, and then we classify the first one, and our metric captures the whole process. Maybe you think now that it's obvious, and it's because I went through the full process before I asked you the question, but we did not take the big picture into account when we work on the project, and we just easily made this error. Here is a comparison of regular precision recall we used originally and the winner precision recall, which is a better metric for our system. And as you could see, we removed some false positives, so the final metrics are better. Second problem we met was a well-known problem of leaky feature. So what does it mean when a feature is leaking? It means that it leaks information from labels, and it's always happening because the feature is using something what is not available at prediction time in production. It can be something from future or just some piece of information from label, and labels are not available in production. Here are two examples I took from internet. You cannot predict year salary from month salary because month salary is basically the same information. And the second example is a bit more interesting because it's a situation when the feature is looking to the future. Because if you predict or diagnose a patient whether he has pneumonia or not, you cannot predict this from information if he took some medicine because it's something he took after he was diagnosed. But you have this in dataset, but it happened after the prediction or after diagnosing by some doctor. In our project, we found a leaky feature as well. It was completely different type of leaky feature. It was somehow surprising. So let me explain. For the model, we use some annotations for training and for measurements as well. But we wanted to enrich our training data with another data. On Zboží.cz, there are people who care about quality of the product database, and they are allowed to force a pairing of an offer to some product. And we have such manual pairings in our business logs. You can see such a log in first row of my table, the blue row. Here's a label 1. But we did not have negative examples for such pairings. So we searched in index for negative examples, and we enriched these business logs with negative data. But there was a bug in obtaining products from index, and it returned products with no category. So for all negative data, there was none in category. And this is completely bad because now from category you can directly tell what is the label. Once there is none, the label is 0, or if there is a category, the product should be paired. And the model found that out when it was trained. And after the training, we saw that the metrics just increased too much. So we got suspicious, asked ourselves what is happening. We took a look on feature importances, and we saw that the feature which captures the category of product is the best one. So we knew that it's bad, something wrong is happening, we took a look to data and we found this leakage. Again, this leakage is happening because positive examples are generated by a different process than negative examples, and the second process got a bug, so it introduced the difference in the processes. The last problem in our project, or the last one I want to present to you, is that we worked with skewed data. When we created annotations, we first sampled from our offer database in uniform manner, but this was just too expensive because in offer database, most of the products don't have a proper product and from in product database, so we had too much negative data in this sample, and for the pairing tool, the positive data are most informative, so we wanted to have as much positive data as possible. So we then took another sample from offers which are already paired to a product in production, and this sample had almost 100% positive rate, so we were happy. We merged these two samples together, and the result was non-uniform data. First, we did not care that we have a skewed data set. We trained the model, tuned the threshold to find some trade-off between precision and recall. You can see here 88% precision and 90% recall. But then we asked ourselves, are we doing the right thing? Are the numbers correct? And we decided to reweigh the data. And what we saw scared us, because the precision dropped by 8%. And what is interesting here, that recall remained the same. And it was a really dangerous situation, because we basically found a threshold to obtain some balance between these two metrics, but the balance was not present. So how is it possible that the recall is the same and precision differs? We have to look on formulae for the metrics. First, I will talk about the table in the right. It's a confusion matrix for binary classification, where we have positive data P, which according to predictions are either true positives, these are positive data predicted as to be positive, and false negative. And the important to note here is that positive data are overrepresented. The second, negative data, the same situation, they are underrepresented. They divide to true negatives and false positives. So let's go to the formulae. Recall, you probably know that it's a ratio of true positives and positives. So we have positive data in numerator and denominator as well. So even if those are scaled by some factor, they are scaled by the same factor, so the recall is the same, and we have like a right metric. But for precision, the situation is completely different, because in formula there are false positives in the denominator, and they affect the number, that the denominator is smaller than it should be, and so the precision is higher and it's skewed, and it corresponds to our observation of drop in precision. And that's all for the last problem in our project. So I can now conclude on the last slide. First, I described what is the pairing tool and what is Zboží.cz, but most important were the practical issues you can meet in your project as well, I think. And we work with inaccurate target metric. And the takeaway here is that you should care about final metrics and not only the low-level metrics of your model. And you might need to adjust like standard machine learning metrics because they might not fit your problem. The second problem, leaky feature, it helped us to be cautious about strong features and just two miracles features and high increase in metrics. And we needed to know what is happening during the data generation process. Data scientists sometimes don't know this process because the data are given to them from someone else, but they should care. And for the third blunder, I talked about there is only one advice: insist on uniformity. And if you do not have uniform data, make them uniform. Sometimes it is not possible to have uniform data. There was a mention by Honza about bandit problems, which are problems where we work with non-uniform data and they are related. Thank you. This is the end of my talk. So now I will answer your questions.
Thanks, Ondra. I will again share the screen. And so far we have one question, which is which of the blunders took you the most time to discover, and which one do you find the most dangerous for the production deployment?
Okay, so thank you for the question. I believe the last one is the most dangerous because it really affects how do we pair our products. We shifted the threshold, and if it's shifted, it means that much less offers are paired. Before we performed much more false positive errors, and it means that the users could see much more issues on the web. And what was the most difficult to find? Let me think. The leaky feature was found very quickly. The skewed data set, at some moment we found out it was not hard to find, but just to realize that there might be such a problem. In fact, it was not hard to find these problems once we started thinking about the big picture.
Okay. In the meanwhile, we got a second question. When insisting on uniformity, the positive samples in training data can be very small, which makes the training very hard. How do you solve this issue?
Yeah, okay. So for training phase, you could use non-uniform data, but the advice is related to the test set and to computing the metrics. In fact, in our project, we did not work with uniform data for training phase.
Okay,
yeah.
Cool.
I hope
Thanks.
I give you the answer.
Yeah, hopefully. So thanks again. Thanks to all the speakers for your talks. It was great to hear plenty of insights to the Seznam's research during one meetup, so that we have some idea. Just to remind a few basic information regarding the MLMU community as a whole. I will just remind you that we have a website, MLMU.cz, Facebook profile, and probably the best place to check our schedule and future meetups or events is our meetup.com profile, which you can find pretty easily. And I believe that you most likely use that to register for this event. And as promised, we are not finishing the whole event yet. I would like to invite you for networking, which is obviously a little bit limited. We cannot offer you any free beers or drinks today, but we are going to split you in so-called breakout rooms, which is a simulation of, let's say, those small groups that usually happen after the talks. In a minute or so, you will see a small window on your screen inviting you to one of the rooms. So go ahead and pick one of them. And there is also one new thing. If you have ever experienced those breakout rooms before, you can now actually even manually change the room if you want to look for one of the speakers and ask a question personally or whatever. So just let me set up the breakout rooms, and it will actually let you choose where you want to go. So pick one of the rooms, and there you should be able to unmute, switch on your camera, and if there are like no English speakers or no non-Czech speakers, then feel free to switch to any language you like. So thanks a lot, and let me switch on the breakout rooms. And if you are on YouTube, feel free to jump on to our Zoom and yeah, and take part in this networking here. So I've just opened the breakout rooms, and you should see a window or something that allows you to pick a room you want to go in. And I'm already seeing people jumping to the rooms. So if you already see the list of the maybe participants and the rooms, pick one of them and jump in.